Let's continue with part 2 of our burglar alarm circuit design. In part 1, we designed this latch circuit, and we said that this latch circuit could exist in two different states. One state is when both transistors are in the off state. And the other state is when both the PNP and the NPN transistors are in the on state. So let's examine both circuits and determine all of the node voltages and all the branch currents. And let's start with the off circuit. So initially, the emitter base voltage on this PNP is 0 volts, and that puts it in the off state. So that means that we have no current flowing in this 2K resistor, and so we also have 6 volts at the base. And since we have no current flowing in the collector, because this transistor is off, this current is 0. And since we have no current flowing through this 10K resistor, by Ohm's law, the voltage drop across this 10K is 0. So we have 0 volts across this 10K. And the NPN is off, so its base emitter voltage is 0. And 0 volts across 10K is no current flowing in the 10K. So we have 0 volts across this 10K. So we have 0 volts at the base of the NPN. We have 6 volts at the base of the PNP. And we have no collector current in the NPN. It's 0. And we have no current flowing in the emitter. That's 0. And no current, again, flowing in this branch. So we have 0 current there. So let's look at the other circuit in the on condition. So the base emitter voltage on the PNP is, by rule of thumb, about 0.7 volts in the on condition. So in the on condition, we can run quite a bit of current in the collector, but we limit our collector current by these two large 10K resistors. So what happens is this PNP transistor goes into saturation, and that means that this collector base junction becomes forward bias, and our collector, rule of thumb, emitter to collector voltage will be about, say, 200 millivolts or 0.2 volts. And if we're dropping 0.2 volts across this PNP and 6 volt power supply, we have 5.8 volts at this node. And we have 0.7 volts across the base emitter of the PNP. So we have what? 5.3 volts at the base of the PNP. And we have a voltage divider. This 10K divides this 5.8 volts, divides it down to approximately 2.9 volts. And rule of thumb for the base emitter voltage is about 0.7 volts. So if we subtract 0.7 from this 2.9, we end up with 2.2 volts at the emitter of the NPN, and 2.2 volts across 1K is 2.2 milliamps in the emitter branch, and most of that 2.2 will end up flowing in the collector. So we have 2.2 milliamps. And this resistor, we have 0.7 volts across our 2K, so we have 0.35 milliamps. And I believe that leaves us with a fair amount of current flowing in our base terminal. If we subtract 0.35 from our 2.2 collector current, we get the base current of the PNP 1.85 milliamps. But there's one thing that we neglected in this circuit, and we neglected the base current flowing in this NPN. And we know that beta of this NPN is defined as the collector current divided by the base current. So if we take the collector current and divide it by beta, we can get the base current. And what I care about is the maximum base current flowing. That happens when beta is at the minimum. And if I look at this NPN transistor specification, the min beta min, equals 40. So if I take this collector current and divide it by the min beta 40, I get the maximum base current that I can expect. And when I do that, this base current comes out, I believe that's 0.055 milliamps. Now that's going to have some effect on this voltage, this 2.9 volts. That's going to tend to drop that voltage down a little bit. And I want to show you a trick how to estimate how much that voltage goes down. If we have two resistors, this is connected to 5.8 volts, and we run a current that's 0.055 milliamps, and each resistor is 10K. This is 10K. The change in voltage at this intermediate node is the parallel combination of these resistors times the current. And perhaps in a future video we will prove that. But just take my word. So if I have 10K in parallel with 10K, the equivalent parallel resistor is 5K. It's half that amount. 5K times 0.055 milliamps gives me the change in voltage at this node. And I believe that comes out .275 volts. So actually my voltage is not 2.9 volts. This base current in the NPN drops that voltage down by an additional 0.275 volts. So that's kind of a lot. I'm not happy with that. So to fix this situation, I'm going to change this 10K resistor value. I'm going to drop that down to 3.3K. And likewise for this other 10K, I'm going to drop that to 3.3K. Now my parallel combination is 3.3K divided by 2. So let's check what that is. That is, so I have the same current, 0.055 milliamps, times my new parallel resistor, which is half of 3.3K, 1.65K. And if I multiply those together, we get 0.09 volts, a little less than 100 millivolts. So I think that's tolerable. So that's pretty close to 2.9. That 2.9 may go down to 2.8, but it's pretty close. So I think I'm happy with this 3.3K. So hopefully this gives you an overview of how to look at the circuit and calculate the node voltages and their branch currents. And now let's get on with the burglar alarm circuit design. Here I've added a few components shown in yellow to my latch circuit. And what these components do is they enable the latch, when triggered, to automatically shut off after about 60 seconds. So let's see how this works. Let's assume that my latch is initially in the off condition. That this NPN is off and this PNP transistor is off. And if that's true, then I have my ground, or my 0 volts, at this node. This is also ground, or 0 volts. This node up here is also 0 volts, or sitting at ground. So if I somehow trigger this PNP into the on condition, the voltage across this resistor capacitor network will suddenly go from 0, it'll jump up to approximately 5.8 volts. Now recall that we are losing about 0.2 volt drop across this PNP transistor when it's in saturation. So when I apply this voltage, this 5.8 volts across my resistor network, the voltage at the top plate of the capacitor, now remember that a capacitor resists change in voltage. So this voltage is going to ramp up very slowly and eventually reach 5.8 volts. And what happens is when this base voltage on this NPN transistor is equal to the base voltage on the other NPN transistor, which when the PNP transistor is on, that base voltage is about 2.9 volts. So when this base voltage gets to about 2.9 volts, the current splits. In this 1K resistor current splits between this transistor and this other transistor. And as this capacitor charges up a little more, the vast majority of the current will now flow in this branch, and essentially no current will flow in the NPN transistor at the left. And when that happens, the NPN transistor at the left shuts off. This collector current goes to 0. When that happens, there's no current feeding the base of the PNP, so this 2K resistor charges the PNP base voltage up to the supply, and the PNP transistor goes off. So everything shuts off. Once the voltage at this node gets to about 2.9 volts or a little more. And recall from a previous video that the time to do this, the time to reach half of the final voltage, is equal to 0.693 times the time constant RC. So if I can adjust R and C to the correct values, I can set this delay time to about 60 seconds. So once triggered, this circuit will go into the on state for about 60 seconds. This capacitor at the right will charge up. When it gets to about 2.9 volts or a little more, the transistor, or the current, is diverted into the transistor NPN at the right and taken away from the NPN transistor at the left. The latch shuts down, and the circuit actually resets itself. Once this PNP goes off, this NPN goes off, this capacitor will discharge through these 3 resistors, and the circuit will reset itself, waiting for an intruder to come and trigger it again. So let's determine the value of R and C to produce about 60-second delay time. So this is kind of getting cluttered here, but bear with me. So the key thing here is that I have to have enough base current, I sub B, to divert all of the current into this NPN transistor at the left. And that current, recall, is 2.2 milliamps. So I want to divert 2.2 milliamps into this collector. And my base current under those conditions, if I assume a min beta of 40, this I sub B is equal to 0.055 milliamps. So I got to make sure that I have at least 0.055 milliamps in this resistor in order to satisfy beta and get enough current switched into this NPN transistor. So when this voltage charges up to about 2.9 volts, I have about 5.8 volts at the top of the resistor. So my voltage across the resistor is 5.8 volts minus about 2.9 volts. And my current must be about 0.055 milliamps. So I can calculate my resistor, R, which is the voltage across the resistor divided by the current in the resistor. When I do that, I get R is about, I think that works out about 51 k ohms. So if I use R of about 47 k, I think that's a standard value. So if I choose 47k, that's a little under, that'll give me a little extra current, and that should be enough to satisfy my beta. So now let's determine the value of C. Now I know that 0.693 R times C is equal to my delay time, which I want to set for 60 seconds. And I know my R is 47k, so I can solve for my C. When I do that, I get C equal to 1.8 times 10 to the minus 3 farads, which is equal to 1800 microfarads. Now, I may want to choose a more standard value for my capacitance. I'm going to go a little higher on my capacitance and make my delay time a little larger. I'm going to go with a standard capacitor of 2200 microfarad. That will probably give me a little bit over 60-second delay, but the delay time is not super critical, so that's good enough. So in our next video, we'll continue with this design and we'll add a few more components. We'll add a triggering circuit and some other components. By Ohm's law, the voltage drop across this 10K is 0. So we have 0 volts across this 10K. And the NPN is off, so its base emitter voltage is 0. And 0 volts across 10K is no current flowing into 10K. So we have 0 volts across this 10K. So we have 0 volts at the base of the NPN. We have 6 volts at the base of the PNP. And we have no collector current in the NPN. It's 0. And we have no current flowing in the emitter. That's 0. And no current, again, flowing in this branch. So we have 0 current there. So let's look at the other circuit in the on condition. So the base emitter voltage on the PNP is, by rule of thumb, about 0.7 volts in the on condition. So in the on condition, we can run quite a bit of current in the collector, but we limit our collector current by these two large 10K resistors. So what happens is this PNP transistor goes into. Let's continue with part 2 of our burglar alarm circuit design. In part 1, we designed this latch circuit, and we said that this latch circuit could exist in two different states. One state is when both transistors are in the off state. And the other state is when both the PNP and the NPN transistors are in the on state. So let's examine saturation. And that means that this collector base junction becomes forward bias. And our collector, rule of thumb, emitter to collector voltage will be about, say, 200 millivolts or 0.2 volts. And if we're dropping 0.2 volts across this PNP and 6-volt power supply, we have 5.8 volts at this node. And we have 0.7 volts across the base emitter of the PNP. Examine both circuits and determine all of the node voltages and all the branch currents. And let's start with the off circuit. So initially, the emitter base voltage on this PNP is 0 volts, and that puts it in the off state. So that means that we have no current flowing in this 2K resistor, and so we also have 6 volts at the base. And since we have no current flowing in the collector, because this transistor is off, this current is 0. And since we have no current flowing through this 10K resistor,